I got locked out of my office, and then I went to security, and they let me in, and then I locked my office door when I came to class. So now I got to crawl back there like a dummy. Will one of you guys go for me? Anybody have any homework questions you would like me to go over? Okay, yeah, for sure. Yes. Okay. Yeah, let's do it. We're so far ahead of schedule, so we can do as many problems as you want. So it's in internal loads. Number 9. Okay. Can I remember all this? No. 1.5 meters, 35 degrees, 10,000 newtons. So it's like, so internal loads, number 9. So it's like a seesaw. The length is 1.5 meters. This angle is 35 degrees. There's a 10,000 Newton force, straight down, right? I think it was straight down, of 10,000 newtons. And that's meant to be at the midpoint between the hinge and the contact at the end. And we want to calculate the internal loads. We're ignoring the weight. One thing about that, when you're doing these internal load problems where you have to use a rotation matrix, on the weekly assignment, I made you do that with the weight as a distributed load, but on these daily problems, I never did. And so on exams, you're never going to have to do those. You're never going to have to deal with the weight on those. Okay. So it's only going to be point forces. Okay, so the first thing we have to do is calculate the external loads. So at the midpoint, there's a force, I'll call it R. Well, how about RA? And then there's a 10,000 Newton force halfway between that point A and the right end. So 10,000. And then there's a contact force, a friction-less contact. So it's going to be perpendicular to the surface of contact toward the chosen body like that. I'll call that RB. And that's all the forces, right? So Since there's no weight, this is actually a case where all that stuff on the left, upper left, is just like cosmetic for the picture. It doesn't even come into the problem. That's kind of funny, but so okay, let's calculate rho, force, moment. I'm going to choose this as the about point, A. So first we have RA. The rho vector is 0. The force vector is RAX, RAY. Cross product is 0. Then we have, so half of this beam is 0.75, so a quarter of this beam is 0.375. We're going to have to do the trig. So if you have a length here of 0.375 and an angle of 35 degrees, then the height there, the vertical leg, is 0.375 times sine of 35. So this is 0.215, and then 0.375 times cosine of 35. This is 0.307. Okay, so that 10,000 Newton force is horizontally 0.307 away from A. So that rho vector is positive 0.307x, 0 for y. Let me make it 0 for y, because I'm lazy, but why can't I do it? Sometimes you do stuff because you're lazy and it doesn't work, but this works. Yeah, exactly, because that 10,000 Newton force, its line of action is along the y-axis, so you can make that y component anything. So this is 0, positive 10,000. I guess I'll use those extra significant figures. So that's 3,072. And then the force RB. So that's 2 times 0.307. So this is 0.6140. Force vector, whoops. I put that as if it was a 10,000 Newton force up. Okay. It is supposed to be negative, yeah. So negative, and so this is negative. And I'm not sure if I would have taken the time to think about the direction of that moment, I would have noticed that that 10,000 Newton force would make it rotate clockwise around that hinge. So it should be negative, so I would have been able to catch that. And then the force vector for RB is 0, positive RB. And so the cross product is 0.614 RB. So Newton's second law says, that gives us our first two equations. And it just says RAX is equal to 0. And then the y equation says RAY plus RB is equal to positive 10,000. And then the moment equation says 0.614 RB is equal to positive 3072. So RB is 5,000. And RAY is 5,000. I guess if I would have sort of thought about the symmetry, I probably could have figured that out. So RA is 0, 5,000. Okay, so now we need to do the internal loads. Let me start by just drawing a free body diagram of the thing. At the midpoint, we have an upward force of 5,000. And then we have that force of 10,000. And then at the end point, another upward force of 5,000. And that's all that's going on. And those are all point forces. All right, so how many of these points are there where the subfunctions can change? 1, 2, 3, 4, so 3 cuts. You probably got this wrong because your stupid calculator was in radians. Didn't you send me an email about that? That's probably why this didn't work.
In physics, like we're doing exclusively.
Yeah.
Unit, and so I just forgot that it was.
I know. That's easy to do.
But I redid the weekly and none of the calculations changed. Like I redid all my calculations.
Oh, okay.
And we didn't really use any angles.
Oh, okay. You did it twice. Okay, and now for the rotation matrix, we're going from a coordinate system like that to a coordinate system like that. So this time that is a negative 35-degree rotation about the z-axis. So a rotation matrix is cosine of negative 35, sine of negative 35, 0, negative sine of negative 35, cosine of negative 35, 0, 0, 0, 1. Okay, so I'm going to plug that into my calculator. Okay, so now I'm going to go, I'm going to multiply this Q matrix to each of these point forces. They're all very simple, just with Y components only. So first I'm going to go Q times the force 0, 5,000, 0. We're actually going to use this one twice. So you get negative 2867.88 and positive 4095.76 and then 0. We can forget about that 0 now. And then the only other force we have to do is the 10,000 going down. 0, negative 10,000, 0 is positive 5735.76, negative 8191.52, and then 0. I actually didn't multiply this by the rotation matrix. You know how I got that? I just multiplied it by negative 2 because, you know, this vector is just negative 2 times the first vector I did.
Oh, okay.
So now we have this. We have the force at the midpoint of negative 2867.88, positive 4095.76, and then halfway between that one and the end, we have 5735.76, negative 8191.52, and then we have the first one again, negative 2867.88, 4095.76. One of these three forces is never going to show up in an internal loads calculation. Which one? Yeah, the one on the right end, our cuts never make it to there, you know. So the first cut, well, I said that we have to do 3 cuts, but cut 1 for x values from 0 to 0.75, everything is just 0. So there's really only 2 cuts that we need to do any calculations for. So now the second cut is from 0.75 to 1.075. $1.125. Okay, so this one, so now we are including this point force of negative 2867.88, positive 4095.76. And then the internal loads. So Newton's second law says negative 2867.88, 4095.76, plus T minus V is equal to zeros. So T is equal to 2867.88, and V is positive 4095.76. And then the moment equation, only the vertical component produces a moment. The moment arm for that is 0.75. So we have 0.75 times 4095.76, and that's a positive moment. And then plus m minus vx is equal to 0. So m is equal to v times x minus oops. Ugh. 3071.82. So m is equal to 4095.76x minus 3071.82. Let's check the derivatives. Notice, I mean, usually we check the endpoints too, but this cut doesn't have any endpoints in it. So dm dx is equal to v. Is dv dx equal to q? It is, because there's no distributed load. So anytime there's no distributed load, what that means is that the shear force has to be constant. So that works. Okay, so cut 3 is for x from 1.125 to 1.5. So we have, for the first force, negative 2867.88, and then 4095.76. And for the second force, I'm not going to remember that, 5735.76. And the y component, negative 81, 91, 52. Okay, so Newton's second law says, so we're adding these two vectors together, which means we get positive 2867.88, negative 4095.76, plus t minus v is equal to zeros. So t is negative 2867.88, and v is negative 4095.76. And then the moment equation, we have positive 0.75 times 4095.76. And then we have, this vertical component is negative, downward. So that's going to be a negative moment. So we have minus 1.125 times 81, 91, 52. Plus m minus vx is equal to 0. And so m is equal to vx and so you get plus 6143.64. And so m is equal to negative 4095.76x plus 6143.64. So dm dx for this cut is equal to v. V is constant, so negative dv dx is equal to q. And now we can think about the endpoints. At the left endpoint, which of these cuts are we in? So the cut that gives us the values for the left endpoint is the first cut. Everything's equal to 0. Well, there's no point forces or point couples there, so that end condition is satisfied. So now let's go to the right endpoint. Which cut are we on for the right endpoint? 3. Yep. So we have to use the equations for cut 3 to check those. We should have non-zero tension and shear force at that point because we have non-zero point forces. And we do. And then the last thing is check the moment. There's no point couple at the right endpoint, so the bending moment should be 0. There's the function for the bending moment, so how do we check if it's equal to 0 at the right endpoint? Wrong. The way you do it is, so What's the x value at the right endpoint? 1.5, yep. So just, we have this function that's valid for any x values in that third cut. So plug in 1.5 into that function, and you get that m is equal to 0, which is what it should be. So all those checks work. That doesn't guarantee that you didn't make any mistakes, but it increases your confidence a bit, you know. If we didn't want to go through the whole rotational Newton's second law, we could have integrated V. We'd have a constant of integration, and then required that when you plug 1.5 into this function, you come out with a moment of 0. And that would be your boundary condition, and you'd get the same answer. Any other questions about that one? Okay. Any other homework questions anybody wants to see? Yeah.
Do you think it would be possible to do this assignment 3 since that's already been done?
Oh, that's a long one, isn't it?
Oh, yeah.
I can't do that. I couldn't finish that in a class period. But if you email me, I'll send you the solution. I think I have done a solution to that already, and I think I did integrate instead of by the way, because the moment equation is so ugly in that one. I think I did integrate V and then find the boundary conditions.
How about number 7?
And that same set that we just did. This one, the horizontal one?
Yeah.
Okay. So 500, 600, and then 1,000. It's 1 meter long. And this one does have a mass of 30 kilograms. Okay, so 500 newtons like that. A couple of 600 Newton meters there. And then a force of 1,000 at the midpoint that goes to the left. And then over here, that's a fixed joint. So we have an R and a MR. The good news about this is we can do we can calculate the internal loads without calculating the external loads for a problem like this. We can skip that step because anytime you have a fixed joint on the right side, none of the cuts depend on those, none of your cuts take into account R and MR. So we can just start right here. I skipped the weight. Let me draw the weight. This thing is 1 meter. It has a mass of 30 kilograms. So 294.3 newtons divided by 1 meter gives you 294.3 newtons per meter for a distributed load. So N for this one, you have the 2 endpoints and you have the force at the middle. The distributed load never changes function. So it's just N equals 3, and that means we have to do 2 cuts. Okay, so cut 1. This is for x from 0 to 0.5. So you have the 500 Newton force, you have the couple of 600 Newton meters. You haven't gotten to 1,000 yet. And then you have that weight distributed load. So this distributed load has a magnitude of 294.3 and a length of x. So the centroid is right in the middle because that's how it is with a rectangle. And the total force is 294.3x. So here's the weight force. And then you have T, V, and M. So Newton's second law says 500, 0, plus 0, negative 294.3x, plus T, negative V, is equal to 0. So T is negative 500. And V is negative 294.3x, and that's all. And then for the moment equation, we have a positive couple of 600. We have a clockwise, so negative moment, with a moment arm of x over 2 and a magnitude of 294.3x. And then we have plus m minus vx is equal to 0. So m is equal to vx plus 147.15 x squared minus 600. So m is equal to negative 147.15 x squared minus 600. So first, let's do the derivative checks. dm dx is equal to v. That's good. Negative dv dx is equal to q. Here's q for the whole thing, so that's good. The tension and bending moment should both be non-zero at the left endpoint. That's non-zero. The bending moment, if you plug in x equals 0, you get something non-zero, so that's good. The shear force should be 0, and you can see if you plug in x equals 0, you get 0, so that all works out. Is this part of the beam in tension or compression? And how do you know? So look at this tension value. If it's positive, you're in tension, it's being stretched. And if it's negative, it's in compression, it's being smushed. So this is in compression, okay? There are some materials that are stronger in tension than compression or vice versa. Not really engineering materials for the most part, but you can find stuff that where it makes a difference in whether the thing's going to break, whether it's in tension or compression. Bone is that way because, really most bones are required a lot more often to support pressure than to support being yanked on, And so bones break more easily in tension than they do in compression. And they're way, way stronger along the long axis than they are side to side because you never ask bones to do that, hopefully. Follow my Twitter for more information on bones. Actually, don't follow Twitter. Twitter's going away. You'd have to follow something else. Me neither, but man, people sure liked it, but not anymore. Life comes at you fast. Okay. Cut 2. So this is for x equals 0.5 to 1. So now we have that 1,000 Newton force in there. We have the 500 here, the 600 Newton meters here, the 1,000. The point force representing the distributed load, 294.3x. You'd figure that out the same way you did in the first cut. And then you have the internal loads, T, V, M. So Newton's second law says 500, 0. Plus 0, negative 294.3x, plus negative 1,000, 0, plus t negative v is equal to zeros. So this time t is equal to positive 500. V is equal to negative 294.3x. And now we go to the moment equation. We have the 600. We have the minus x over 2 times 294.3x plus m minus vx is equal to 0. This is the exact same equation we had before. So we know we're going to come out with the same answer. So m is equal to 147.115x squared negative, and then minus 600. dm dx is equal to v. Negative dv dx is equal to q. And at the endpoints, everything should be non-zero. And if you plug 1 in for x, that's what you get. And on this half of the beam, is it in tension or compression? Tension, yep, because it's positive now. And so where is this thing most likely to break? Where would you think this would be most likely to break? It's easiest to see always if you graph these things out, but
Obviously, that's attached to the wall.
yeah, that's right. Yep. Any other questions about that one? Okay, well, now we're sort of behind, but we're going to spend about an hour doing new stuff, okay? No, not really. That's a joke. Okay, that's the end of class. Next time we'll talk about square threaded screws again. Okay, have a good weekend.